freezing point depression is a colligative property. So remember, in freezing point depression, what happens is the solute gets in the way of a solvent. So say like the salt would be the solute, water would be the solvent. The salt gets in the way of the water, so those hydrogen bonds can't line up because the salt molecules keep messing with them. And so they can't line up. And so it's getting colder and colder and colder, and the hydrogen bonds are trying to line up, but those salt molecules keep messing with it. So it's still getting colder and colder and colder. Eventually, those hydrogen bonds will find a way to line up, but now the freezing point and the temperature has gone down. So before they line up all pretty and perfect, the temperature has gone much further, much lower than it normally would have. And that's freezing point depression, and that's a colligative property. Again, it doesn't depend on the identity of the solute, it just depends on the number of things. So remember, when we're doing this, this here is the change, whoops, this is the change in. Change in. So this is the change in the freezing point. That's what this means, change in freezing point. It's not the new freezing point, but it's how far the freezing point went down. This is a constant. This will always be given, and it's different for every solvent. We almost always use water. Pretty much always use water, but it's always given to you. This, remember, this is the Van Hoff factor, I. This is the number of things. And that is our molality. So remember, what is molality? Molality is moles of solute, I can spell, solute, over kilograms of solvent. Remember, the solute less of the solvent, more of. Whichever one there's more of, that's your solvent. Whichever one there's less of, that's your solute. So if we have salt in water, there's more water than salt. Water is the solvent. Salt is the solute. Remember, I is the number of things. Again, what does that mean? It means the number of things it breaks up into. So for example, if we have NaCl, and remember when we did these dissociation equations a while ago, right? This breaks up into two things, Na plus and Cl minus. So its Van Hoff factor would be 2. If we had CaCl2, when it dissociates, it breaks up into Ca2 plus and 2 Cl minus. So it breaks up into 3 things. So its Van Hoff factor would be 3. Now again, in Chem 101, they'll give you, like, usually they give you a more precise one. So if they give you a more precise one, use that one. But this is our best estimate of our Van Hoff factors. Okay, so let's try this problem. What is the freezing point of a 1.7? Remember, little m, that is molality. Little m is molality. Big M is molarity. Big M is what we're doing in lab, molarity. We're not doing big M, we're doing little m. Little m is molality. So what is the freezing point of a 1.7 molal aqueous ethylene glycol solution? And first thing we need to look at here is, well, what kind of problem is this? And so again, I'll have all of these equations listed, but you have to go, oh, this is freezing point. This is a colligative property. Oh, our equation, I need to look for this equation, KBIM. I need to look for that equation. That's the equation I need to use. Again, you don't need to memorize this equation because it'll be on the board, but you do need to know when to use it. You do need to know what all these things mean. And that goes for the whole entire exam. Okay, so we're given a 1.7 molal solution. They're asking for freezing point. So I need to figure out the new freezing point. And so in this case, again, my equation is delta TF equals I M KF. And again, doesn't matter which way. Now I is the number of things. But look, this is a molecular compound. When this dissociates, it doesn't dissociate. It's just one thing. So in this case, I is just one. So we can just ignore it. Because all nonmetals, non-metal, right? Non-metal, they do not dissociate. They stay together in water, right? They do not dissociate. So I, in this case, is just one. Again, this KF, that is our constant, always given for you. The constant for water is 1.86 degrees Celsius per mole. Okay, so when we do this problem, we need to figure out, well, we have our molality. Nice, we don't even have to find it. So we just need to plug it in. So we just need to use our equation. So if our molality, so delta TF equals our molality, which we don't even need to find because they just gave it to us, 1.7 baby M, times our constant KF, 1.86 degrees Celsius per molal. Units, and we get, I don't know what we get, whatever that is when you multiply it, 3.2 degrees Celsius. Now, it wants to know what the freezing point is. This is not our freezing point because we're talking about water, an aqueous solution. Whenever you see aqueous solution, aqueous means in water. So this is ethylene glycol in water. Well, water freezes at 0, right? This is a freezing point depression. So our change in our freezing point is 3.2 degrees Celsius. So if water freezes at 0, it's going to go down by 3.2 degrees Celsius. So our new freezing point is negative 3.2 degrees Celsius. So remember, this is the change in. This is how much it goes down. So it goes down by 3.2 degrees Celsius. So our new freezing point is negative 3.2 degrees Celsius. So a lot of times people go, oh, that's my answer, I'm done. Nope, not your answer. That's the change in, that's how much it goes down. Your answer is whatever your freezing point is minus that. And so for water, I'll never give you the freezing point of water because I'm just going to assume that you know it's 0. I'm also going to assume you know that water boils at 100. Those are assumptions I'm making and telling you, you definitely need to know water freezes at 0 and boils at 100. If it was any other substance, I would give you the freezing point or I would give you the boiling point. But for water, I'm assuming you know 0 and 100. Okay, so I have this all meter for you. So I have all these solutions, by the way. The reason I do all these solutions twice is so when I do post those lecture solutions, here they are for you. This is much nicer than my awful, horrible writing, right? And so again, that's where these lecture solutions come in and they're so handy. All right, so any questions on this one? Questions on this one? No? Okay, so let's try another one. Just there's something wrong with your next slide. I just want to fix it really fast. There you are. Now it's prettier. Okay, so let's look at the next one. There we are. You couldn't see the constant. I just fixed it. So this one says, calculate the molar mass of a compound if a solution of 12 grams is dissolved in 80 grams of water, freezes at negative 1.94 degrees Celsius. The KF for water is 1.86. Okay, so handy dandy things that can help you with your exam. Number one, if you see this KF, look for that equation. Delta T change is I M KF. Why would this constant be given for you if you weren't using this equation, right? Have you ever heard the words like use the test to take the test? use the test to take the test, right? That's when you see this, you're like, oh, that constant. Oh, there's the equation with that constant. I think I should use that. Yes. Now, this one wants molar mass. So we need to remember molar mass is grams over moles, right? It says calculate the molar mass of a compound if the solution of 12 grams dissolved in 80 grams of water freezes at negative 1.94 degrees Celsius. Okay, so I don't think there's any way we could know this I, so we're just going to assume it's 1 because there's literally we couldn't do both. We have KF, and they're telling us the change. So the change is 1.94 degrees Celsius. That's how far it goes down by. I don't know molality. Because the reason I don't know molality is because remember, molality is moles of solute over kilograms of solvent, right? Well, they give me 12 grams and 80 grams. Well, I can convert this, right? I can convert this to kilograms, but I can't convert this to moles because I don't know what it is. So I don't have my molality. I have my constant they gave it to me, 1.86 degrees Celsius per molality, per molal. So if I just divide this by 1.86, again, let's say, I don't know where I'm going. I don't know. All I know is I can figure out molality. When you're doing these problems, you don't need to know the end point here. You just need to keep going through the process and follow one step, next step, next step, next step. And eventually, hopefully your units all work and you get to your correct answer. All I know here is I don't know how to get to my molality. I mean, I don't have my molality, so I'm just, I don't know, try to get to my molality. 1.86 degrees Celsius per molal. Okay, this crosses. I don't know what this is. I'm sure I did it over here. Let's just get our answer and I'll come back. 1.043. Oops, sorry. My molality equals 1.043 baby M. Now remember, what is this? 1.043 moles of solute. Let's just write that again. Solute over, we'll just say 1 kilogram of solvent. Okay, so we've got our molality and we want our molar mass, right? Molar mass. Okay, so let's think about this. Okay, grams over moles. Well, they're giving me grams. So I just need to figure out the moles of my solute, right? So if I have, just gonna make some more room right here. If I have 80 grams of water, and that's my solvent, 80 times 10, well, let's just do it the long way. I have 80 grams of my solvent. And there's 1,000 kilograms. Oops, 1,000 grams in 1 kilogram. And molality, again, is 1.043 molal per kilogram. Sorry, moles. Okay, so in 1 kilogram, there's 1.043 moles. Oh, that'll get me to moles, right? So it's just a unit conversion of using this, understanding that's my solvent. And remember that baby M means moles solute over kilograms solvent. So do you remember when we used, well, and we still always use molarity? Remember when we used, we said molarity is moles over liters, and then we put it into a unit conversion? We're just doing the exact same thing with molality. We're just saying it's moles over kilogram and putting it into a unit conversion. So it's the same thing that we did with molarity, it's just different units, but the process of using it, exactly the same. Okay, so let's look at this all neater with actual calculations done. Okay, So we got our freezing point. Now, a lot of times people will try to put this negative in the problem. Remember, the freezing point went down by 1.94, right? So the change in the freezing point is the regular freezing point minus the change. So it's not negative because the freezing point was 0. The freezing point of water was 0, and it went down by 1.94, right? So this is going to be a positive number. FYI, it's always a positive number. So in short, if you have a negative number, change it to positive. So we get our molality, and then we use unit conversions where we cross off our kilograms. It's exactly what I just did. Now we've got our moles. And then we just use the definition of molar mass. Molar mass, grams over moles. Our grams was given in our problem, and we solved for our moles. So what is our molar mass? 144 grams per mole. So this one's like I don't know, I think this is probably the hardest question you can get with freezing point depression. Usually they're really just straightforward, but this adds this little, what was added here? This was added right here, using molality as a conversion factor. That's what we added. We added molality as a conversion factor. Okay, so those are our colligative properties. So we have 3 colligative properties. We have vapor pressure lowering, boiling point elevation, and freezing point depression. Those are our 3 colligative properties: vapor pressure lowering, boiling point elevation, freezing point depression, right? So make sure you know all those. And again, those are in your Chem 101. And I want to remind everyone, right, to be eligible to drop your lowest lab exam and quiz, you need to finish all of your Chem 101 homework with passing grades, right? Which is like 75 or better on each of them. And you can't, the reason I say that is because people were like, well, I did them all. You got a 2%, but yeah, you did them all, right? So you need to complete all of your homework. And so you'll practice a few of these in your Chem 101, and it'll also really, really, really help for your exam. Okay, next thing we're going to talk about is Henry's law. So Henry's law is talking about the solubility of gases. So in intro chem, you probably talked about the solubility of solids, right? Like how you get things to like dissolve faster, right? You heat it or you shake it. I mean, we've kind of experienced solubility in our lab, right? When we made our unknown for our titrations, right? We swirled it and we swirled it, we shake it and tried to make it dissolve, right? But what about if it's, and those are solids, but what about if it's a gas? How do you get gases? What is this? How do you get gases to be more soluble, right? How do they get bubbles in our soda, right? How does that work? Well, that is Henry's law. Okay, so we're going to talk about how gases dissolve in liquids. So the solubility of gases is pretty minute, pretty small, and it's directly proportional to the partial pressure of the gas above the surface of the liquid. And this is called Henry's law. Now, the equation for Henry's law is this, pretty simple. So the C, this is just the maximum concentration or maximum solubility of a gas in a particular solvent. KH is the constant. Again, constant always given to you. And then our last one is our partial pressure of our gas. This is the partial pressure of our gas. So how big this KH is, so again, it's different for every compound. This reflects both the differences in the intermolecular forces and the gases and the deviation from ideal gas behavior. Now, important to know, the solubility of gases and liquids decrease as the temperature of the liquid increases. Okay, so let's talk about this one's kind of a big one. Think about your soda, let's just use soda. When you go to like McDonald's or Burger King or Wendy's or wherever your favorite, or Chipotle, wherever you go and you get a soda, right? You put ice in the cup, right? Put ice in the cup. When it comes out, it's cold. Why? Because to get gases to become more soluble, the colder it is, the more soluble the gases are. And now think of it, if you leave your soda out on the table, it goes flat, right? Why does it go flat? Because the molecules get more energy the warmer they are, and they escape into the air out of the liquid. So the colder it is, so I'll say like the colder it is, the more soluble the gases are. Or you could say the warmer it is, the higher to the temperature, the lower the solubility of our gases. Right? Now, this is actually really important. So there are rules and laws and regulations for power plants. And one of the laws says that it limits the temperature that they can expel into waterways. So into like oceans, rivers, and lakes. There's specific maximum temperatures that they can expel into rivers and lakes. Why? Because if the temperature is too warm, the dissolved oxygen in the water decreases. Because if we increase the temperature, the amount of oxygen in the water decreases. Well, what do fish use to breathe? Oxygen and water, right? If there's not enough oxygen, the fish die. We've actually seen this in Southern Orange County, not from power plants, but you know when it gets really, really, really hot? When it gets really, really, really hot, the lakes and the rivers and things of that sort, the temperatures, well, pretty much our little man-made lakes, right? The temperatures get really high, and that decreases the amount of oxygen in the lake. And then the fish don't have enough oxygen to breathe, and they die. This is all based on Henry's law. Okay, so let's look at a question in Henry's law. So this is a lake in Peru. It's 3,800 meters above sea level. The average pressure up there is about 0.63 atmospheres. Remember, the higher we are, the lower the pressure, right? So here we are, lower pressure because we're high. During the summer, the average temperature of the water surface rarely exceeds 15 degrees Celsius. What is the solubility of the oxygen in the lake at that temperature? Now, this is kind of an important piece here. Air is about 20% oxygen. So the air we breathe is about 20% oxygen. Okay, so how are we going to do this? Well, we need to figure out what the pressure is above the solution. And it says air is 20.95% oxygen. And then we need to figure out the solubility of the gas. Okay, so how are we going to do this? All right, so we have a few things. So we're asked to determine the solubility, which is the maximum concentration of oxygen gas in water at 0.363 atmospheres and 15 degrees Celsius. That's what we're asking. So we're going to use Henry's law here and to figure out the partial pressures. We're going to need this constant, right? Gonna need that constant. Gonna have to give that constant to you. Remember, this is a constant. All constants are given. So we need to figure out what is the partial pressure of the oxygen, right? To get to this solubility. And so we need to figure out the partial pressure. How are we going to figure out the partial pressure? We're going to use this. Remember, this is Raoult's law, which we talked about last week. And so we need to figure out it's going to be the mole fraction of the oxygen in air times the atmospheric pressure, which is given. And that's how we're going to figure out our solubility. Okay, so you can kind of see my equations up here. So here's those two equations. Should have probably changed it to white. And here's everything they gave us. Here's the KH. So I'm giving you the KH. So first of all, this is the overall equation we're going to use. That's what they want. But we need to get this. That's what we need to figure out. So what does this mean? So let's use Raoult's law first, because we need to get here to get there. So Raoult's law, again, is the pressure. And in this case, we want to know the pressure of our oxygen. It's going to be the mole fraction of our oxygen times the pressure of total pressure, right? This is going to be pressure of our, I'll just say atmosphere, pretty much. So our mole fraction is 20%, so 0.2095 times the pressure of our atmosphere, which is 0.636, right? It's the part we want. So you want the oxygen out of the hole. So the pressure of all molecules in the atmosphere is 0.636. All of them in the atmosphere is 0.636 at that height. Oxygen is 20% of that. So of all of these molecules, oxygen is 20% of it. So there's our oxygen times all our molecules. So that gives us 0.133 atmospheres. That is the pressure of our oxygen. Okay? So that's our pressure of our oxygen. So now we can use our Henry's law. So Henry's law, so we want the solubility of our oxygen is going to be the constant, the Henry's law constant, which is always, again, going to be given to you, times the pressure of our oxygen. I'm going to write over here for make it a little bit easier. So again, this is given to you 1.5 times 10 to the negative 3 moles per liter atmospheres times our partial pressure of oxygen, which is going to be 0.133, right? I'm just putting this here, atmospheres. I ran out of room. I'm going to run out of room here. Okay, well, I'm going to be writing really small in a second. Okay, so now our concentration here, so atmospheres. Put this in your calculator, you get like 2 times 10 to the negative 4 moles per liter, right? Moles over liter. So this is our concentration. Usually concentration, and in the problem, let me see if they asked this one. Yeah, they did. In molarity and milligrams per liter. Ah, that's annoying, right? But it specifically asks milligrams per liter. Right now, we've got molarity. So here's our answer in molarity. Check there. Milligrams per liter, it's not so bad. So this is already in liters. All we need to do is get to moles to milligrams, right? Think of this, moles to milligrams. We can go from moles to grams, molar mass, and then we just go from grams to milligrams, 1,000 milligrams in 1 gram, right? So we can do this all in one piece, which I'll do-ish over here. I'll try it. 2 times 10 to the negative 4th. And now I'm just going to use this as a conversion. Moles over liters. And in 1 mole, let me just see if I can fit oxygen in here. Moles of oxygen, right? And in 1 mole, there's 32 grams of oxygen. And in 1 gram, there's 1,000 milligrams. So we've got moles, grams, milligrams per liter. This is what I didn't want to do, but you can see there. So they're kind of on top of each other, which gives you 6.4 milligrams per liter. So you're becoming like stoichiometry kings and queens here when you're doing some of these problems. Now, if the problem didn't ask us for milligrams per liter, we would have been done here. Okay, so again, what did we do here? So this whole thing, we needed to figure out the pressure of specifically oxygen. They gave us the whole pressure of like every molecule in the atmosphere, but they asked oxygen. But then they said oxygen is 20%, 21% of all of the molecules. So we had to figure out using Raoult's law, well, I need the oxygen part, just the oxygen part. So we got our oxygen part, which was 0.133. Then we use Henry's law. It says R-O-U-L-T, Raoult's law, and then we use Henry's law to figure out our concentration. Okay, so any questions on this one? You're good on this one? Yes. Oh, well, here you are. Here's pretty much everything. This one's a little bit, let me just leave it here. I'll show you the other one in a second. The other one's kind of convoluted in the way I solved it. Okay, any questions on this one? Questions here?